So the other field that we're going to go ahead and derive how the electric potential energy changes as you move charges around within that field is for an electric field due to point charges. So again, if I come back to my definition for the change in the electric potential energy, so that's negative some integral from some initial position to some final position of the electric force dotted in with my infinitesimal little displacement vectors. And so let's take our picture here where we've got Q1 and Q2. I'm going to move Q2 and I'm going to move it away from Q1. All right, so I'm going to increase its distance away from Q1. Let's let both Q1 and Q2 be positively charged, and so I know that the electric force is going to point away from Q1 that's acting on Q2. So again, these two charges, if they're both positively charged, they're going to try to repel each other. So the electric force on Q2 points away from Q1. So what is it that these two charges want to do? Well, the electric force acting on them, if they're repelling each other, is that they want to push these charges away, right? And so I know before I do any math that if I choose to move Q2 farther away from Q1, then I'm moving in the direction of the electric force, which means that the electric potential energy has to be decreasing. So that's going to be our check when we get to the end of this derivation and we have an equation. That's what we're going to check to make sure that our equation makes sense. So if I come back to this equation, let's initially think about this dot product. Well, FE and dr both point in the same directions. So in terms of this dot product, I can basically reduce this to just the magnitude of the electric force times this infinitesimal little distance dr. And so the magnitude of the electric force, if that force is due to point charges, is given by Coulomb's law. So here I can plug in kq1 q2 over r squared times this little differential element dr, and now I need to integrate from some initial position to some final position. Well, again, kq1 and q2, these are all constants, so I can pull those out of the integral, and so I'm left with the integral of 1 over r squared. The antiderivative of that happens to be negative 1 over r. So a couple things. One is now I notice I've got two negative signs here that are going to cancel out, one for my antiderivative, one for my definition for the change in the electric potential energy. And then I need to evaluate my integral from some initial to some final position. So when I do that, I'm left with this final answer that says the change in the electric potential energy here is equal to k q1 q2 times this term in parentheses, 1 over r final minus 1 over r initial. So if I think about that r final and r initial, so if I move away, that means that r final is greater than r initial. So I've moved to some larger distance than where I started. R final is greater than R initial. That means 1 over R final is less than 1 over R initial. And so I'm taking something smaller and subtracting something bigger, so this term within the parentheses is actually negative under that situation. Since K, Q, and Q, those are all positive, sure enough, this term being negative inside the parentheses means that the change in the electric potential energy will be negative. Pulling my like charges apart will decrease their electric potential energy. That's moving in the direction of the electric force here, which means the electric potential energy decreases. That's what my equation also tells me. If, on the other hand, I push them together, so now the final distance between Q1 and Q2 is smaller than the initial distance, so I move them towards each other. Well, now this term in the parentheses is positive, and so in that case I'm going to have a positive k, a positive q1, a positive q2, and this term in the parentheses is also positive if I move them closer together, which means that the electric potential energy is increasing. And since I'm moving against the electric force and moving them closer together, sure enough, that's what I expect. So pushing my like charges together will increase the electric potential energy. So here's my equation then for calculating the electric potential energy, how it changes when I have an electric field due to point charges. And so R initial and R final here are defined to be the initial distance and the final distance between my two charges. So to be clear, these are not components. They're defined to be distances here. They're always positive when we're plugging into this equation. If we want to talk about the electric potential energy, again, we must have a 0 point. And our equation basically tells us that the 0 point is going to occur when our two charges are infinitely far away. So the 0 point for the electric potential energy is going to be when the distance between them is infinitely far away And then so I can calculate the electric potential energy, and really this is the electric potential energy relative to the 0 point when they're infinitely far away, is given by K Q1 Q2 over this distance R12, where that's just defined to be the distance between the two charges. So some important points to emphasize about this equation. One is, again, R12 is defined to be a positive distance. The second thing is that the electric potential energy can be positive because I have K is always positive, R12 is always going to be positive. So if my charges are the same, whether both positive or both negative, then the electric potential energy for them being some finite distance away from each other will be positive. And again, all that's saying is it was 0 when they were infinitely far apart. They want to move away from each other. The electric force wants them to repel, and by bringing them together, whether they're both positive or both negative, I had to do work to move them against the electric force. So the electric potential energy can be positive if they're the same charge. It can be negative if oppositely charged, or it's 0 when they're infinitely far apart. So with just two charges, I still have all three options in terms of the electric potential energy being positive, negative, or 0. The electric potential energy depends on two charges, which is like the electric force. So we talked about two vector quantities, electric force and electric field, one of which depended on two charges, the other one which only depended on the source charge. Here's something that also depends on an interaction between charges. So the electric potential energy depends on an interaction between two charges, just like the electric force. Number 4. We don't want to take the absolute value of Q1 and Q2 to calculate the electric field. So this is not like our equation for calculating the magnitude of the electric force, where we did want Q1 and Q2 in absolute values. Here we don't want them in absolute values. So again, the signs of Q1 and Q2 will simply plug in as they are, which again will help dictate whether or not I have a positive or negative electric potential energy. 5. In terms of thinking about the difference between the electric force and the electric potential energy goes like 1 over R rather than 1 over R squared. And this is an easy mistake to make in terms of calculating things out. So just make sure if you're doing electric potential energy, you only have a single R on bottom rather than R squared. And then the last thing to remember is that this is a scalar. It's not a vector, right? So energy is a scalar. It's not a vector quantity. Why that matters is when we start having multiple charges, we want to add up the net electric potential energy due to multiple point charges as scalars, not as vectors. If I want to calculate the electric potential energy of one charge in the presence of multiple others, so here I'll calculate the electric potential energy of Q1 in the presence of Q2 and Q3. So again, there are two interactions that I need to keep track of, one between Q1 and Q2, the other between Q1 and Q3. But in keeping track of them, all I have to do is add them. So I'm going to have two terms, one for each interaction. They're both scalar quantities. I just add them together as scalar quantities. If I want to now think about the electric potential energy of the entire system, so Q1, Q2, and Q3 make a three-charge system, I can calculate the electric potential energy of the system by including all of my interactions. So when I thought about the electric potential energy of Q1, I just included the electric potential energy due to the interaction between Q1 and Q2 and a second term for the interaction between Q1 and Q3. But if I want to talk about my three-charge system, I also need to include the interaction between Q2 and Q3. So my system has three terms. One telling me what the electric potential energy is relative to the 0 point infinitely far away between 1 and 2. The second term between 1 and 3. The third term between 2 and 3. So including all my interactions lets me figure out what the net electric potential energy is of my system. Now what this is equal to is it's basically telling me that the electric potential, the energy I have, is the energy that's been stored from the work that was required to build the system of charges. So when we brought up Q1, let's say we bring up Q1 into empty space, that requires no work. There's no charge that's either attracting or repelling it. When I bring up Q2, there's an interaction between 1 and 2, and so I have to do work against that interaction. When I bring up Q3, now there's two interactions. So there's the interaction between 1 and 3 and the interaction between 2 and 3. And so again, it's keeping track of all the work I have to do as I build that system that tells me how much electric potential energy is stored within a system of charges.